Welcome to this Vodcast about inverse functions. Um, you probably have a pretty good idea of what inverse means already. You're familiar with things like addition is the inverse of subtraction and division is the inverse of multiplication. And you might have the idea that square rooting is the inverse of squaring, and we'll talk a little bit more about that particular case in a minute. But that's the idea of inverse, and we want to particularly talk about inverse functions. Um, One example that I always give is if I'm driving down the street and I roll down my window and stick my head out and wave at somebody, the inverse of that, of course, would be to pull my head back in from the window and then roll up the window. And the order in which I do those things is kind of important, as you might imagine. Okay, so inverse means getting back. When we apply the inverse, we get back to the original state that we are in. Here are some things, objectives that we're going to look at in this podcast. Determine if a function is invertible, and I'll explain in just a second what invertible means. And we want to look at inverses graphically. How can we determine if two functions are inverses of each other by looking at their graphs, or how can we produce the graph of the inverse from the graph of a function? That's pretty easy to do. And lastly, being able to find the equation of a inverse algebraically. So if we know a function, if we have the algebraic form of a function, how can we produce the algebraic form of its inverse? Okay. Invertibility. So if something is invertible, if a function is invertible, it means that a function, its inverse, is also a function. Okay. Here are a couple of other ways of describing that, or these are synonymous terms. A function is invertible if it passes the horizontal line test. So I'll show you what that means when we look at graphs. And invertible, if a function is invertible, if it is a one-to-one function, you know that a function for every input there's exactly one output, and one-to-one would mean for every output there's exactly one input, which isn't true of all functions, but it is true of invertible functions. And another description of invertibility is they are monotonic. So you might not know what monotonic means, but let me show you a couple of graphs that are monotonic. This graph here, typically an exponential graph, is monotonic. In other words, it's rising, it's always rising. Or a graph that looks like this is monotonically decreasing. It's everywhere on the graph it's decreasing. What I mean by something passing up above, I talked about passing the horizontal line test. Well, you know that a function passes the vertical line test if I can draw a line, and it always passes everywhere I move that line. It only passes through the graph once, both of these graphs. Let me get rid of one of these graphs so it's a little clearer here. So this graph is monotonic, and it's a function because it passes the vertical line test, but it's also a one-to-one function because it passes the horizontal line test as well. So every time I pass a horizontal line through this graph, it only crosses the graph once. So it passes both the vertical and horizontal line test, which means that it is invertible. More details on that in a minute. Okay, two functions are inverse. Here's a sort of somewhat informal definition of inverse. Two functions are inverses of each other if one undoes the other for all values in each domain. So in this case, are f and g inverses of each other? Let's take a look at this. Let's just do it by plugging in some numbers. So f of 3 is equal to 3 squared, which is equal to 9. And so here's what it means, to check this out. If I plug 9 in here, do I get back to 3. And in fact, yes, the square root of 9 is 3, so that worked. Put in 3, got 9, put in 9, got 3. That means that's the inverse relation that we're looking for. Let's try this with another value. How about the f of negative 3? Well, that is negative 3 squared, which is 9. And then when I do g of 9, if I do g of 9 again, well, I get 3 again. I did not get negative 3. This is not invertible. So the answer to this question is no, not invertible. Okay, well, let's look at some other, let's look at the graph of this for a second too. Here is the graph of f, this blue graph. Does that pass the horizontal line test? No, it doesn't. And if you inverted it, like I mentioned before, graphically, the inverse, they are reflections over the line y equals x. And those are inverses of each other, but you can see that the green graph is not a function. So the blue one was not invertible. So you cannot call f and g inverse functions of each other. Okay, let's get rid of those. And let's look at some other functions that are invertible. Now this is very related. Here are two functions. Now they look kind of like familiar things. H of x is equal to x squared, but we're restricting the domain to x is greater than or equal to 0. So here's what that graph looks like. Is that graph invertible? Is that function that's described by h, is that an invertible function? Yes, it passes the horizontal line test, and it already passes the vertical line test. Okay, so the red graph would be the inverse of that. And by the way, this notation, this -1, that means inverse. That's the notation for inverse. So I can designate two functions as related to each other by the inverse relationship by using that -1. And you're familiar with that on your calculator from, in geometry, we used inverse sine and inverse cosine, inverse tangent when we knew a ratio value and we wanted to find the angle, which is the inverse of knowing an angle and finding the ratio value when you press the sine button. If you want to find the angle, you press the inverse sine button. Same idea. Let's look at this with a table of values. Let's just take some values and plug them in for x in h of x, and I plug in 0 and I get out 0, and I plug in 1 and I get out 1, and I plug in 2 and I square that and get 4 and 3 and 9, etc. And when I do that in the inverse, this table looks ugly here. See if that fixes it. Oops. When I do that in the inverse, okay, I'm back. I had to pause so I could fix this table. When I do this with the inverse, when I put in 0, I get out 0. The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. So look at these tables of values. Inverse is just flipping the x and y values around. And you can see that in the graph. You can see that in the table. And that's what we want inverse to mean. So this is all very nice. Alrighty, moving along here. So graphically, two functions are inverses if their graphs are reflections of each other over the line y equals x. And let's go back and look at that graph again. That's exactly what we had here. That green line is the line y equals x. And even when I did it with the original blue and green graphs, they were also reflections over the line y equals x, but they weren't both functions. And now these two things are invertible and they're inverses of each other. So graphically, you can tell two graphs if you fold on that line, if it looks like it's going to fold up on itself. And also, really important idea about graphing is if the point 0, 0 is on one graph, the point 0, 0 is going to be on the other graph. If you want to plot some points for the inverse, if this point is 1, 1, then it's going to be on both graphs. If this is the point 2, 4, then 4, 2 is going to be on the graph of the inverse. So you can plot points really easily to plot the graph of an inverse, even if you don't know its equation. So numerically, that's this idea. Numerically, two functions f and g are inverses if for every point a, b that is on f, b, a is on g. That's what I just said. If 2, 4 is on h of x, then 4, 2 is on h inverse of x. And algebraically, two functions, this is a formal algebraic definition of inverse. Two functions f and g are inverses if f of g of x, the composition of these functions, gets you back to x, and likewise if g of f of x is equal to x for all values of x in the domains of f and g. That last part is important. So here are these two functions again. That means I should be able to compose these functions with each other. What does h of h inverse of x look like as the composition of functions? Well, I take the inside function, which is the square root of x, and I square it, and that gives me x. So that's what's supposed to happen. I got x out. If I do h inverse of h of x, that means I put this function inside there and I take the square root. Now, when you take the square root of x squared, remember from algebra, you're supposed to get the absolute value of x. But my domain was x is greater than or equal to 0. So I don't get the plus or minus that I normally would be when I take away the absolute value, because I'm already designating that x is greater than 0. So I get x out. Okay, so that's working algebraically on that domain. All right, so what if we have a function and we want to find the inverse of that function algebraically? You probably remember this from algebra. You simply switch x and y around. So let me write this as a y equals equation. I take this and I switch x and y around, and I get y plus 4, 3 times y plus 4. And you undo this thing algebraically. You solve for y. So I divide by 3 first. I'm going to square both sides and get x squared over 9 is equal to y plus 4. And then I'm going to subtract 4 from both sides and I get x squared over 9 minus 4 is equal to y, which is, we could now designate as f inverse of x. That should be the inverse. Graphically, I can, again, let's emphasize it. So if the point negative 4, 0 is on the graph of f, this being f, then I should be able to graph 0, negative 4. That point's on there. And it looks like 0, 6 is on this graph, so 6, 0 is going to be on the graph. I'm going to put in the line, I'll do it in pink here. I'm going to put in the line y equals x so I can see this. A point that is on, so it looks like that point right there. And I don't have any other really great points, but my graph should look something like that. They should look approximately like reflections over the line y equals x if I did a good job. And there you have it. So that's how you find it algebraically, and you should check your results when you're done. So I would like you to pause this and find g inverse of x with this example. Okay, you're back. Um, you should have done this. Should have switched x and y around and got 2y. This is a pretty easy one. Nice linear equation. X plus 5 is equal to 2y. X plus 5 divided by 2 is equal to y, which you could write, if you prefer, as g inverse of x is equal to 1/2 x plus 5 halves. Now let's check to see if those are really inverses of each other, because if that's true, it should be that g of g inverse of x should equal x, does it? Let's do g of g inverse of x. That would be, take the g function, which starts with a 2, and plug in g inverse, which is 1/2 x plus 5 halves, and then minus 5. That's g of g inverse of x. Distribute, and you get x plus 5 minus 5, which is equal to x. It also should be true, you should be able to check it out this way, g of g inverse of x, g inverse would be 1/2, and then plug in g of x plus 5 halves and see if we get x. We better get x, otherwise they're not inverses of each other. So distribute, and I get x minus 5 halves, and plus 5 halves, and this is equal to x. So they are inverses of each other. Yay. Okay. Have fun.